Hello, everyone. I'm Jennifer Bly, Director of Marketing Communications here at the PyTorch Foundation. Welcome to our webinar on accelerating DLRMv2 inference on Arm Neoverse CPUs with PyTorch. We're so happy that you have joined us today. If you have any questions, please share them in the comments wherever you are viewing from, and we will address them after hearing from our speaker. I am pleased that we have a special guest with us today, Annop, who is a principal software engineer focused on performance optimization and ML acceleration on Arm Neoverse CPUs. He specializes in low-level optimization, advanced vectorization, and hardware-aware technologies to enable efficient ML workloads. Annop leads efforts to enhance PyTorch performance on server-class Arm CPUs, bridging ML frameworks with next-gen Arm infrastructure. Please take it away, Annop. Welcome.
Yeah, thank you. Thank you for the introduction. Hi, everyone. Today, I'm going to speak about how my team at Arm helps accelerating the deep learning recommendation model on Arm Neoverse CPUs. First, let's speak about motivation a bit. Why accelerating recommendation model inference is so critical today. It is no doubt that recommendation systems play an important part in defining our digital experiences nowadays. The recommendation models are used in many industries, ranging from e-commerce, finance, streaming to advertising and social media. These systems are driving how we interact with content, products, and services online. And for example, in e-commerce, it suggests products you may like. When you open the trading app, for example, maybe you see suggestions for stocks that you may be interested in. In streaming services, it helps selecting what films you would like to watch next. In advertising, it helps showing content which are more tailored to your interests. And in social media, sometimes you see notifications suggesting people you may know. The recommendation systems analyze vast amount of data from user behavior, product data, transaction logs, and etc. It generates real-time predictions to personalize user experiences. And all this has to happen under tight latency and throughput constraints, and as you can imagine, at a massive scale. In fact, a study from Facebook in 2020 found that inference dominates the operational costs in its data centers. Recommendation models alone account for nearly 80% of all the AI inference cycles in their production systems. And imagine if we can accelerate these models even by a small percentage, it translates to a huge operational cost reduction. Plus, faster inference means improvement of user satisfaction and better engagement. So why do we focus on CPU for this optimization? Because CPU is everywhere. They are cost effective. They are available in the cloud and on the edge. Large systems come with large memory capacity for storing embedding tables, which are found in many recommendation models. For online inference, batch size is usually small, so the workload is more memory bound than compute bound. And doing inference on CPU means that no data is needed to be transferred between the host and the accelerator, which helps reducing the latency of the inference. And in this talk, I will focus on the DLRMv2 model, which is a leading model architecture for recommendation. And I'll show how we can significantly accelerate its inference. Let's take a look at the architecture of the DLRMv2 for a bit. This model is designed to handle two distinct types of input features. First, the dense features, which is like continuous values, for example, user age or the time of the day, and the sparse features, which are typically categorical data like user ID, product item ID, or user geolocation. The dense inputs are first processed through the multi-layer perceptron, which does nonlinear transformations of the continuous features. And on the other hand, the sparse features are handled by the embedding layers. In DLRMv2, it has 26 embedding tables to convert sparse categorical IDs into dense vector representations. And this step is key because it allows the model to operate in a continuous space where similarities can be captured more effectively. The outputs of the dense features and the embedding layers are then combined into single outputs and passed into the dense sparse interaction layer model as a deep cross network. After the feature interaction layer, we feed everything through another MLP called the top MLP, which processes the final representation to produce the model output, which is like probability of user click. Yeah. So for running the benchmark today, we use the MLPerf framework. MLPerf is maintained by ML Commons organization, which provides standardized benchmark to evaluate ML workloads across different hardware and software stacks. It ensures that the comparisons are consistent and fair, reproducible across multiple vendors and platforms. Meta contributed their MV2 model under the ML Common initiative, and they provided official pre-trained model weights. So it's much easier to reproduce results and focus on optimizing inference performance. For the input dataset, we are going to use the critical terabyte dataset, which is one of the most massive real-world datasets in online advertising. It contains like click data, 24 days of click data, and the first 23 days of data were used for training. For validation, it uses the first half of the last day of data, and the second half of the day 23 data is used for calibration. Next, we are going to discuss about optimization strategy in the benchmarking framework and also model optimizations. First, let's discuss about the parallel inferencing strategy. So instead of introducing parallelization at the ML operators level, in the model, we choose to parallelize at the query level to achieve better scaling and CPU utilization. So we start with a large incoming query from a load generator or a load gen. This query is then split into smaller tasks, which are put into a task queue. from there, we spawn multiple worker processes, and each worker process is pinned to a single CPU core on the system. These worker processes then process tasks in the task queue in parallel, and the results are then aggregated and sent back to the login, and this completes the inference cycle. Using this parallelization strategy, we observe good scaling with the core counts on the system, and this allows us to process a high number of queries in a scalable way. So we further optimize inference latency and throughput by applying model quantization, converting the weights and activations from 32-bit floating point to 8-bit integers. We use the PyTorch eagle mode quantization, in which we manually insert quantization and dequantization operations at the critical point in the model graph. Specifically, we quantize the dense feature inputs before passing them into the bottom MLP. The output is then dequantized before combining with the outputs from the embedding layers. This is then requantized again before being passed into the feature interaction layer and the top MLP. The output from the top MLP layer is dequantized before producing the final prediction after the sigmoid function. So this quantization results in the model size reduction by approximately a factor of 4, which significantly improves the memory bandwidth and the cache efficiency. For the quantization scheme, for the embedding tables, we quantized, we use weight-only quantization per channel with the UIN8 data type. And for the MLPs and DCN, we used per tensor quantization with UIN8 activations and int8 weights. And in both cases, we used the min-max observer to get the quantization parameters during calibration. One of the main bottlenecks in the recommendation model is the linear layers found in the MLPs and DCN. For these linear layers, we leveraged optimized kernels in Arm Compute Library, or ACL, taking advantage of the innate matrix multiplication instruction capability in Arm Neoverse CPU cores. Furthermore, to minimize the library's overhead to reach the optimized kernels, we add a direct path from the PyTorch A10 library to ACL, bypassing the Intel Deep Learning library and the 1DNN library, which were previously called for this operation. This direct path to ACL is also enabled for the quantized addition operations in the DCN layer, which helps to improve the performance further. Another performance critical part of the DLRMv2 is the embedding lookup operation, especially with large tables with high cardinality, sparse features. In DLRMv2, we deal with multi-hot encoded inputs where multiple indices per feature need to be looked up and summed. The largest table in DLRMv2 processes a 100-way multi-hot encoding. And to accelerate this layer, we implemented a custom vectorized embedding lookup kernel using advanced SIMG neon intrinsics into PyTorch. In this kernel, after the table lookup indices, the innate weights are loaded into vector registers, widened and converted to 32-bit floating point numbers. And at the accumulation step, we use the fused multiply add instructions to maximize the throughput during the dequantization. Finally, after applying those critical optimizations, here is the benchmark result for offline benchmarking mode in MLPerf for DRMv. For the DLRMv2 running on 64 areas Graviton 4 cores. So we observed significant speed up with our parallelized inferencing strategy, and a further 14x speed up from leveraging optimized kernels in ACL and the kernels we implemented for the embedding lookup. From the cost efficiency standpoint, this performance numbers translates to about 0.5 US dollars per 1 million recommendations. This number is based on on-demand price of Elvias C8G 16X large instance type in the EU West 1 region. So these results highlight strength of ARM-based CPU, not just from the raw throughput standpoint, but also the cost efficiency and energy-aware compute for large-scale recommendation inference. So to summarize, we have walked through the key steps to accelerate MLPerf DLRMv2 benchmark on Arm Neoverse CPUs. We started with discussing our parallelization, the parallel inferencing strategy, which helped us to fully utilize the CPU cores and boosted inference throughput. Then we also discussed about the quantization technique that we applied, converting the model to from 32-bit floating point to 8-bit integer to reduce the memory requirement and increase the compute efficiency. We also discussed how we leveraged optimized matrix multiplication kernels in Arm Compute Library, and how we implemented the custom vectorized kernel for the embedding lookup with the advanced and SIMD neon intrinsics into PyTorch. I would like to highlight that the optimization for the matrix multiplication and the embedding lookup is now available in PyTorch 2.7. If you would like to try the setup yourself, try running the benchmark, you can head over to the Arm learning path, which I have put the URL here. It contains setup steps, details, how to run the benchmark, whether you use cloud providers or on-prem system, it will work. Thank you very much for your attention, and now I'm happy to take any questions you may have. Thank you.
Thanks, Annop. Any questions? We'll open the floor. Let's see, we have one here. to get us started. What are some of the features of the ARM architecture that you take advantage of or that are used in your optimizations?
Yeah, as I discussed, the main one is probably the innate matrix multiplication instruction capabilities, which are found in the Arm Neoverse cores. Yeah, that's the main one.
Great, thanks. And I'll just let everyone who is watching know if you have a question for Anoop, please drop it in the comments and we will answer it live. Next question. Will the techniques you apply here work on any ARM-based server like Graviton in AWS, Cobalt in Azure, and Axion in Google Cloud?
Yes. Yeah, as I showed, yeah, we have results for areas Graviton 4, which is based on Arm Neoverse v2 CPU cores. Google Axion is also Neoverse v2. Microsoft Cobalt 100 is Neoverse N2. But it also contains the same capabilities as V2. Yeah, so yeah, these optimizations apply for all the cores that you find in major cloud providers nowadays.
Great. Next question. Are the optimizations for DLRMv2 complete, or are there more enhancements you are working on in the future that we should stay tuned for?
Yeah. Well, in my opinion, optimization work is hard to say that is complete because you can always optimize for more. We may have something that we plan for in the future. For example, yeah, in the future, maybe we can leverage the matrix multiplication kernels in the ARM Clyde library, which may help to increase performance and reduce the library's overhead even more, because then it's the direct path from the A10 library and the optimized kernel.
Great. I will put one last call out for questions. Drop those in. And I see we have another one here. Are there other use cases, models, or frameworks beyond DLRMv2 that ARM has optimized with similar techniques? And does this approach apply across use cases?
Yes, yeah, this optimization is general. Yeah, for example, the optimization for the innate matrix multiplication is applicable to any transformer-based models. Any models which contains linear layers. But yeah, the optimization, the custom kernel for the embedding table lookup is maybe more geared for the DRM model or recommendation model with large table lookups.
Great. All right, I'm not seeing any additional questions. Is there anything else that you wanted to cover or discuss, or maybe how to get in contact with you? Anything like that?
Yeah, not much. Yeah, I just would like to say thank you very much for everybody's attention, and please stay tuned for further optimization. Our team is working hard to make ML workloads run efficiently on Arm CPU cores. Thank you.
Well, thank you so much. We really appreciate it. Fascinating discussion here. For everyone tuning in, make sure you check out our website, pytorch.org. Be sure to subscribe to our newsletter and follow us on social media, including X, Facebook, and LinkedIn. And then you'll be the first to know about our future webinars. Thank you so much for joining us, and have a great rest of your day.
Thank you.
Bye-bye.
Bye.